first thing, I would like to thank all the colleagues that participated in organizing this competition. It was a big pleasure to work with you for almost 3 years, actually, because of the delays caused by the pandemic. And in particular, I would like to thank Tammy for her incredible work. It was a really pleasure to work with her. So thank you. And I would like to thank all the participants, all people that somehow contributed to this challenge. And so now let's announce the results. But before announcing the results, I would like to show a few slides about what this phase 2 means. Let's go on. So the CVRP and VRP with time windows tracks, it was different from the other tracks because it was a 2-phase competition. So we had a phase 1 where we run instances from the literature, and the runs are performed by the competitors themselves in their own machines. So we have to use the pass mark scores to normalize the times. But then the best competitors in each track, they were invited, they advanced to phase 2. And the idea is that in phase 2, we will use new instances not known by the competitors, and the runs are performed by us in identical Dynamax machines. And in that way, we expect to reduce, not completely eliminate, but to reduce a lot the overfitting effect because the instances are new, and avoid the difference from the time normalization because the pass mark scores are only averages, so they do not they're not perfect, they're just proxies on the speed of a machine. So in our competition, we used this measure, the Primal Integral. So for each test instance, what we do is that we compute the primal integral of the solver over that instance. And so we use a best known solution for an instance. We use the starting point, not a solution, but a value which is 10% higher than the best known solution. And we assume that the solver will find a sequence of n solutions, and we will record the solution value and the time. And we will compute this value, the primal integral. That is actually quite simple. So it's something like this. Each time you find an improving solution, this is recorded. And the primal integral is the area behind this curve. Actually, it's normalized. So, but essentially is the area behind this curve. And the idea of this is that a good solver should be able to provide fairly good solutions quickly to avoid having a large area in the beginning, but should also come very close to the best known solution and in order not to have a large area in the tail. So Primal Integral is designed to try to measure two different things. So the overall, actually the overall behavior of the method. And we have a score system that we borrow from the previous challenge, the Steiner challenge. And we follow the Formula One, Grand Prix Formula One score system. And for each instance, we have the primal integral of each solver, and the best solver, the first place, gets 10 points. Then the second gets 8, 6, 5, 4, 3, 2, 1. So, and then we will add the points, and we have the final rank of each solver will be based in this score system. And we have to develop, in order to compute the primal integral, the controller, the software that Tammy mentioned. Actually, this software runs only on Unix, based operating systems. But what's the idea of the controller? Well, the solvers can be written in any language, but they are assumed to print each improving solution. As soon as they find an improving solution, they should print it to the standard output stream. And the controller will start the solver process, okay, and will keep listening to the standard output using a Unix pipe. So the solver will print the solution, and immediately the controller will get that solution, will check if the solution is really feasible, will compute the actual cost of the solution. If okay, that solution will be used for computing the primal integral. Controller also kills the solver process if the time limit is reached, or if there are several instances from the literature where the optimal solution is known. And when the solver reaches the optimal solution, controller kills the process because there's no hope to improve that solution, so to save computing resources. And another feature of solver is that if the solver process crashes for some reason, the controller does not crash and still computes a valid primal integral. So this is a sample of the controller output. Okay, so the controller, this is the name of the competitor, not a real name, but a Wolverine. This is the operating system. This is got automatically from the system. This is the processor, automatically got from the system. Host ID. This is the passmark single thread benchmark of that processor. And this means that there will be a time factor of 1.18. So the times in that machine, so we use as a baseline machine with passmark 2000. So that, for example, the time limit of 1,800 seconds in that local machine actually will be this one, because we use this factor here. Here's the best known solution for this instance. In this case, this is known to be optimal. And the output continues here. So every time a solution is found, we record that this is the time where the solution was found. This is a quite easy instance. So the optimal solution was quickly reached in a little more than 1 second. And this is the primal integral, okay, for that run. And so the controller was coded by some undergrad students from the Federal Paraíba, Bruno Passetti and Rodrigo Ramalho, and Eduardo Uchoa from now in RIA, postdoc in RIA, contributed, and the code is available here. I think it's a useful code. And the controller outputs, and we have tons of files of because many instances were run from many competitors, they were analyzed with the scripts written by João Marcos Pereira Silva, who is a PhD student at our university. Okay. And in CVRP Phase 1, we used the X set, so 100 instances from 100 to 1,000 customers. Those instances were built in order to have a very diversified set of attributes: depot positioning, customer positioning, demand distribution, average route size. Some classic instance from the literature here. One interesting set, a recent one, is this set here, the Belgian set. So 10 instances from cities in Belgium. They are very large. They have from 3,000 to 30,000 customers. And we had the contributed instances. There's another contribution to the challenge, the contributed instances, because the literature instances, all of those instances, they use Euclidean distances calculated from the customer coordinates. And actually, the only reason for that is because this is convenient for having a small instance file, because in order to store 30,000 by 30,000 matrix with actual distance is too large. But we did that for the new contributed instance. They have actual distances, And so we have the Logi. Logi is a Brazilian logistics company. They provide a number of instances. Actually, they have this repository they call Logibud, where they have a large data set of real, not only vehicle routing, but also facility location instance. I would like to thanks to José Carlos Maldonado from Logi. And those instances correspond to problem defined in 3 metropolitan areas in Brazil: Belém, Brasilia, and Rio de Janeiro. So this is one of the instances. This is my city, Rio de Janeiro, but I actually live here, Niterói. So I live and work here. My university is here. I live here, not very far. This is a bridge. This bridge is 13 kilometers long. So Rio de Janeiro is a very non-Euclidean city, as you can see, because we have islands, we have a bay, we have a bridge. This gap here where there are no customers is a forest. There is a tropical forest inside Rio de Janeiro. Okay. And so this is an interesting instance to test if the methods can handle distances that are very far from Euclidean. And we have Ortec. They Walter Koo very kindly also contributed with instances from Rio US grocery delivery service. So we had now 12 new instances. We call the Dynamax set of all of those instances. They have a real the map distance, real map, not Euclidean distances. And so all the instances are now in CVRP lib. Here are the Dynamax instances. Okay. And for VRP with time windows, we use the very classic instances by Solomon, 56 instances with 100 customers, and 300 instances from Homburger and Gehring. So the very classic. But there is one important detail here. The competition, we are assuming that the objective is only to minimize the total route length. But part of the literature, in particular the heuristic literature, assumes that first you should minimize the number of routes and only then the total route length. But we are using this assumption, this convention here. And now we have the new, this happened today, okay? So those VRP with time windows instance are now available too in CVRP lib. Okay, that's and for example, this is an instance here with 600 customers. So the depots here in the center, here are the customers. And actually, due to the time windows, look, the routes are not so beautiful as a CVRP routes because the vehicles have to take into account the time windows, and this is the best known solution for that particular instance. I would like to thank Ivan Xavier, Araújo de Lima, Federal Tocantins, and Eduardo Queiroga, now in RIAB, for their work on CVRP lib. And so let's go on to the results. So we start with VRP with time windows, phase 2 results. And this is phase 1. This is phase 1 results. So the phase 1 results are this. Actually, we had 12 active competitors. That means competitors that actually sent their results. And so the 7 best competitors advanced to phase 2. So those are the teams and the solvers that made part of phase 2. Okay. And so now let's see the phase 2 results. Well, how are the phase 2 instances? Because they're supposed to be new instances. Actually, they're not so new. We actually, but this is, it was already specified in the competition rules a long time ago. But we took the Homburger and Gehring instances and modified only the depot. So the depot, instead of being always in the center, now it's in a random location, and this changes somehow the instances can be considered as new instances. And here are the results. So the winner for this track was the team Walter Cole, formed by Walter Kuh from Ortec, Thomas Visser, Joep Olde Unic, Jald van Horn, Camille Cornelissen, Ernst Roos, and Pin Eichenberg, sorry for my pronunciation. And the corresponding paper is a hybrid genetic search for VRP with time windows, a high performance implementation. So let's congratulate to this team for very good results that were obtained. And here are the actual results. Okay, so we had in second place the team Hust Smart, and then Alkite X, then Vavavuma, ALNS++, Log WFPB, and WFI. So that was the, so here is the score in the number of points. Our rank is based on the number of points, but we have some side statistics that are useful. So the average primal integral and the median primal integral. But I would like to show you something interesting, is that, okay, in this competition, the router, the name of the solver, got quite better overall results. But if we consider particular classes of instances, we may better understand the relative strengths and weakness of each solver. For example, 1/3 of the instances are clustered. So the customers are not randomly distributed, they are in clusters. And for those instances, actually the rank is different. So Hust Smart obtained more points in this subset, Alkite X also, and Walter ranked 3rd. Okay, the difference is not large, but this is significant. So I think there is a wealth of results to be analyzed. We can understand why this particular method may perform better or worse in this or that particular kind of instance. So there are lessons to be learned from this. And now we proceed to the CVRP Phase 2 results. Again, we start with Phase 1 results. So we had 16 active competitors and 8 teams that ranked the first 8 ranked teams advanced to Phase 2. And how are the instances of Phase 2? So we generate a new set of 100 instances between 100 to 1,000 customers. This set is very similar to the X set because we use the same generator code, but we changed the random number generator seed. So the instances are statistically similar, but the actual instances are different. And here is the result. So the winner was the team Alkite X. Right? Sorry for the pronunciation again. Shibiao Jiang, Zhu He, Weibo Lin, Fudama, and Zipeng Liu. And their paper was titled FHC Solver Fast Hybrid CVRP Solver. And here are the results of Phase 2. Okay. So here we have our rank based on the points here, and we have those side statistics here, the average primal integral and the median primal integral. And in this CVRP track competition, so the competition was very tight, the results are very close, and we have a lot to gain from deeper analysis of the results. Okay. So if we consider particular classes of instances, we get many insights of the relative strengths and weakness of each solver. So I will show a few. First, let's divide the results in two sets. So the smaller instances, the 50 instances between 100 and 330 customers. In this particular subset here, we have very close here. It's a tie between this method, UFFIC and AlkadeX. Then we have those two methods here. And what those four methods they have in common? All of them are based on AGS. All of them are based on AGS. So AlkadeX is an hybrid method and uses AGS for smaller instances, exactly those ones that are here. So those methods obtained the best results on the smaller instances. And if we look at the other 50 instances, so the instances between 336 and 1000, we have a quite different picture. So the best method now becomes the AILS here, then AlkadeX. So AlkadeX won the competition exactly because it's a robust method that obtains good results on all sets. And then in third, we have this method route 2 that's not based on this method here. It mixes AGS with Philo with other original ideas. But this method here is based on Philo, and actually the scores are similar. So this is interesting. Another analysis here is let's split the instances in a different way. So let's split between instances with short routes and instances with long routes. With a short route, where we took 50 instances where the average route size, the best known solution, has less than 12 customers, and the remaining 15 instances are the instances where the average route size is larger or equal to 12 customers. So for the short routes, we get this rank here and those statistics here. While for the other set, we had a quite different rank and quite different statistics. And again, AlkadeX won the competition exactly before it got a robust performance over different classes of instances. And that's it. I would like to thank you all for your participation, for being here. I'd like to thank in particular the finalists, all the finalists that because those two tracks, they are very classic problems. It's really difficult to obtain good results because so many people have already worked exactly on those variants. So you need to be brave to try to beat the best existing methods. And my analysis that I just show you is that yes, it's part of the fun of the competition to indicate a winner, but we have several lessons to learn from those results, and different methods they perform, especially in CVRP. We have different methods that perform better on different classes of instances, and then we may soon obtain even better methods by combining those ideas, by doing all those things. And to finalize, I would like to say that I'm quite happy with the state of the art that was reached on those two variants, two problems, because now we have not all companies are Amazon, where they have many thousands of deliveries to do every day in every city. There are many, I would say most companies, they have to deliver to less than 1,000 customers in a day. And this competition shows that we have actually several methods that can obtain very good solutions in quite short times. And in this competition, for the sake of leveling the playing field, we only allowed a single thread. So by only using several cores in your computer, then this means that in seconds you can obtain quite good solutions. So I think this is good news. This is a result of, as in the Gendreau talk, 35 years of development. And so now I think we are ready to really handle those problems in practice. So I think that people in industry should know about that. They should not use the methods that are not so good. The methods presented here are so good that there are no reason for not using them in practice. And then, so I would like to thank you all again. If you want to make some questions, I may answer them too. So thank you very much.
Eduardo, so if we, after seeing these results, if we wanted to make the best of the best method, a kind of Franken GS, CLS thing, we should probably go for HGS for the smaller instances, on the combination of Philo or AILS for the largest cases. And this is a recipe for solving extremely well these 100 instances. Is this correct?
Yes, perhaps. Yes. In fact, the winners, the Alkyd X, they already did a very good job of hybridizing AGS with Philo. But now we know that this can be done even better. We can do even better. And yes, I think so. I think that we have different methods that are better for different, and if we go deeper and we start analyzing by other features like the average route length, if the demands are like this or like that, and we may get even better results. So for sure.
This makes me think a bit. It has a feeling of the SAT state of the art, like SATzilla currently, which combines a very large number of techniques. Ultimately, I have the impression that we can always do a little better by making things more complex. And you always have to make a choice of where to stop. When is the right point to find in the trade-off between complexity of the code base and performance? What is your feeling on this?
Well, I think that all those very highly performing methods are very complex, all of them. And so there are no really simple methods that perform that well. And I don't think this is necessarily bad from a user point of view. I think that, okay, if we have a very complex code, but a code that can handle several variants and is easy to use, I'm okay with that. But I don't know. I think this can be, of course, simplicity is a feature, but this competition showed that if you really want the very best results, you need to use complex methods. There's no other way.